So if you have a straight wire carrying current, so this is the current, and if you're asked what is the magnetic field like around it, it's going to be right hand grip rule. So whichever is straight, put the thumb for that. So represent the straight thing with the thumb, and so that's going to be the magnetic field. So the magnetic field around it is going to be like that. This is the magnetic field. You know, the symbol over here of giving a little space implies it's going behind. That's why we leave a space there just to let you know that this is the front and that's the back. Otherwise, if we just simply like loop it completely, it will not be clear. So this is the and we don't normally represent like this all the time. We just say, all right, it's in here, so we put a cross. It's out here, so we put a dot. So the magnetic field is into the board here and out of the board here. Is that clear? Now, if the same wire is now turned into a circle, the current is going like that. What do is you apply the same rule again. See, the current is going up, so put your thumb like that and find out what's the magnetic field here, which way? In, and here, out. Do the same thing here. Put the thumb in the direction of the current. Which way is the magnetic field here? In, out, in, out, in, out. Right? So using the right hand grip rule, you can see so the magnetic field inside here is all in. So the B is going to be straight in at the center of the circle. So to get the strength, to get the direction of the magnetic field, you use the same right hand grip rule now. But so in this case, which one is the one which is curved? I is curved. So use these fingers for current. So if the current is like that, which way is magnetic field? Into the board. Right? You understand that? And in this case, if the current is going like this, it is magnetic field like that. So both these fingers can be used for both. So if this is current, this is magnetic field. This is current, no. This is current, this is magnetic field. And if this is current, this is magnetic. So whichever is curved is going to be used by these fingers, represented by this. Whichever is curved and whichever is straight is going to be the thumb. Is that clear? So right hand grip rule simply tells you the direction of the magnetic field. The direction of the magnetic field is represented by the current. Now, I spoke a little bit about dia, para, and ferromagnetic materials, right? We'll get back into that soon. And one other thing that you must have seen in the video is this. Be near an infinitely long straight wire carrying current. The magnetic field near an infinitely long straight wire carrying current is what? So if you have a current going in this conductor in that direction, which way is the magnetic field here? So the moment you are given a question asking for directions, you need to use these rules. Like this is a right hand grip rule, immediately use it. Okay, so which way is it? In. And the strength of the magnetic field is what now we are trying to think about. The strength of the magnetic field here is caused by the current not only here. So we are using this, like representation, but will this current cause a magnetic field here? Yes. So basically, there are little current elements everywhere. And each current element is going to create a magnetic field at this location. So how do you find the total magnetic field at this point, the overall resultant magnetic field at this point? You've got to sum up all the effects from all of these, and then you get the answer. So the whole procedure is actually done using calculus. So the equation is derived by using calculus. We're not deriving the equation, but I'm just writing down the equation. Magnetic field strength near an infinitely long straight wire carrying current. So that's why they kind of show it by dotted lines. Infinitely long, straight wire, carrying current is given by this equation. And as I said, this is derived by using calculus. Now why calculus is to come here? Because we are summing up all the little magnetic fields that are created by each and every segment at this point. Make sense? Right? Yeah.
Does the 2 pi come from like the area of the wire? Where does that come from?
2 pi comes in, well, I'll tell you, what is mu naught?
Coefficient of static friction.
Yeah, mu naught actually is, the 2 pi comes in because there is a circular connection to electric current and magnetic fields.
Okay.
So that's where it comes in. But anyway, the more than that, you'll see it later on. Actually, when you go through the derivation, you will actually see more than that. Now, mu naught is called permeability of vacuum or air. For vacuum or air, it's approximately the same. And it's called permeability. What is the other constant that we saw in electric fields? Permittivity. So this is permittivity of vacuum or air. What is the meaning of permittivity? How well electric lines can actually pass through the material, right? How nicely electric fields can actually go through the material. That is basically this. Well, this is also telling the same stuff. How well magnetic fields can go through the material. So permeability and permittivity kind of represents the same, but they use different terminology here just to differentiate between the two parts. So if you come across the term permeability, you immediately understand you're talking about magnetic fields. And the word permittivity immediately refers to electric. Okay, so it is pretty much the same thing, just the term difference. And of course, this one, you know, is 8.85 10 power minus 12, right? Units. This one is 4 pi times 10 power negative 7 units. And I'll tell you what those units are. We'll see the units later. Mu naught is the permeability of vacuum or air, which is 4 pi 10 power minus 7. So what are you going to substitute here is 4 pi 10 power minus 7. So actually this 2 pi will become 4 pi. You get it? So now, again, as I said, what is A standing for? A stands for? Not here.
Perpendicular distance.
The perpendicular distance. In other words, how far are you looking into it? So this thing, yeah, A stands for acceleration, but not here. This is the, or you can use any term. You can use D, you can use X, you know, it's up to you. So some books use A. I don't know this book. Use this. They use R. So every book is kind of different. Some books use A and some books use R. So yeah, I'm using A. The shortest distance from the wire to this thing, basically it's the distance. How far is B? How far is this point where you're trying to find the magnetic field? That is A. Now, we said infinitely long, straight wire, right? So this wire is supposed to be infinitely long. That's kind of a relative term. Look at this wall. Look at the wall. The wall, is it infinite or finite for you? It's a finite wall because you can see there and you can see there. You can see both ends. So if you try to look in terms of angle, because in calculus you need angles. So that that end of the wall is going to be there, and that end of the wall is there. So you can see the angle stretches from one value to another value. That's why it's finite. When is it infinite? So this wall is finite for you because of the angle of view. You can see the whole wall, right? Now, imagine there's an ant sitting so close here, or a fly sitting so close here, and you ask the fly in English, what kind of wall is this? Is it infinite or finite? Then the fly will look that way, can't see the end, that way, can't see the end. So for the fly it is infinitely long, right? Same way this wire will be close to infinitely long, depends on where you are. If I'm going to take this point somewhere here, then that wire is not going to be appearing infinitely long. So when you do this derivation using calculus, we actually take angles into account. So we start this angle here. So this current element is at this angle, and this current element is at that angle. And when you take limits, we take the limits from 0 to pi. Get it? If this is truly infinitely long, if you want to regard that as infinitely long, you're going to take the limits from 0 to pi. So this is 0, and that thing is pi. That's why, so that is basically what we do, and then these are the position vectors. So every element has got a contribution here. Every element makes its contribution. It's like saying, imagine I give you similar looking magnets, okay? And I give him the magnet, and everyone is going to face the north pole towards me. Imagine everyone is like pointing to me like that with the magnets. And I'm here. So what is the overall magnetic field over here because of all of you? Is it just because of this person? It's a sum of all of it. Well, he's going to influence me more. And he's going to push me that way. So his magnetic field is going to be that way, but weak, right? And that one is going to push me this way, but weak. So each of them will have a component pushing me. Which way is the final overall magnetic field? No. In terms of this example. That way. That way. So overall push I'm going to get from everybody is that way, right? So this magnetic field is basically derived using calculus, and after putting the limits from 0 to infinity, this is what you end up as the end product, and that's what you have to remember. So mu naught I over 2 pi a, so mu naught stands for this, and I stands for the current, and a stands for the perpendicular distance of the wire. Where is it? And well, the moment you say infinitely long wire, just blindly take this. You don't have to worry about whether this a is big enough or small enough. Infinitely long, that's it. So if you are using this formula for a wire that is not really infinitely long, that means you're not getting exact values. That's it. So if there's a wire that is this, as long as it's stable. If there's a wire that is as long as it's stable, and I want to find the magnetic field here, is this table infinitely long for this point? No. That means the angles are not really going from 0 to pi, so there are limits there. I mean, like, it's not perfect. So you will get an answer using this formula, but it won't be proper. It will be more or less. It will be like the answer that I get by using the formula for this wire that is this long at this point. Will I end up getting an answer? If I'm going to blindly apply this equation, will I get an answer which is more than the real or less than the real? Why do you say more?
Because you're measuring for, like, if it's infinitely long, you're measuring for more than the
So if I'm going to blindly use this equation, I'm going to get a magnetic field which is bigger than the actual, because the actual, there's no current element in that section. There's no current element in that section. But we are imagining it to be there, right? So if I use this equation, I may get a bigger answer, but in reality the answer can be slightly smaller. Make sense? That's the only issue by using this formula. I'm going to come back with this. What is mu naught? It's a permeability of vacuum or air. Now, it's not always going to be mu naught, like there is going to be a material here. So if there is a material, then we have to bring in what? Mu R. What is mu R? Say it again. Relative permeability. Yeah, just go back to the previous chapter. You can just pull it up. So what is mu? Mu is mu naught mu R. Mu will be mu naught mu R. So this is the actual permeability of the medium, and the actual permeability of the medium will be affected according to this number. For vacuum, what is mu R? 1. For vacuum, it is 1. For other materials, it's going to be different. So remember this. So if I'm going to say, all right, this wire is surrounded by some particular material, then what is the magnetic field here? It's not this equation now. It's mu naught times mu R times I over 2 pi r. So we're going to replace this. So this is only for air or vacuum, which is normally going to be the situation. If there is a strange situation where the medium is definitely different, then you'll be told and you'll have to use that. You can't just stick with mu naught because mu naught is only for vacuum. You get it? So what is mu R? It's called the relative permeability. Like how many times bigger is the permeability in comparison to that of vacuum? And here's where you should come back to the 3 different materials, magnetic materials I taught you about. What are the 3 magnetic materials? Dia, para, and ferro. Dia, para, and ferromagnetic materials. These are 3 magnetic materials. Now what happens if I subject them to different fields? So if I have fields going like this, if I have fields going like that, a diamagnetic material is one which tries to kind of repel off the fields. It goes against the magnetic field. It doesn't like magnetic fields passing through itself. So what happens is the magnetic fields will kind of run away. And like that. And what happens when it comes to para? Para is something that does not repel. It kind of allows magnetic field to pass through, but not so strong. So it increases the magnetic strength a little bit. So it's like that's the para. So compared to here, which is just mu naught, can you see that here it is slightly more congested? And over here it is less. And ferro is a material that accepts everything for itself. It's very strong. Basically everything in that area will pass through it. It welcomes all the magnetic fields to pass through it. And that is a ferromagnetic material. And you can see the strength over there. The permeability is pretty strong. So to compare the permeabilities, over here, the permeability, relative permeability is just less than 1. That is why outside is mu naught, but inside is less than mu naught. Right? With numbers like mu r is approximately like 0.5, something like that. So a diamagnetic material, I think we saw the examples, diamagnetic materials such as mercury, bismuth, and all those things, they will have a relative permeability less than 1 because they try to avoid magnetic fields coming in. Para A paramagnetic field, paramagnetic substance takes a little extra in. So mu r is just more than 1, like an example 1.2. So normally, if a magnetic field is able to pass through, it will now kind of increase it by a little bit, not too much. You can call it a magnetic material, but it's not very quick in responding to it. It's okay. It allows. This one is ferro, which actually is much bigger. So mu r is much greater than 1. And approximate values of mu r, they're all in hundreds, like 300. A ferromagnetic material such as this can take in a lot. The strength of the field can be multiplied a lot more by the presence of ferromagnetic material.
So would a paramagnetic material would it have the permeability of like 5?
Para?
Or yeah.
I mean less. I mean it won't be like too much. Like even 5 is more, I'd say. Just faint. But it does not repel, attracts. So if I take a diamagnetic material like this, okay, this is a ferromagnetic material, right? If I take a strong magnet and keep it next to it, even if it is like this, if I keep it next to it, what will happen to this? It will quickly align itself and get stuck, right? Yes? That's a ferromagnetic material. So what happens is immediately it'll want to take everything through itself. It wants to make all the magnetic fields come through itself. Now if I take a paramagnetic material and keep it like that and put a magnetic field, then it will like deflect slowly. It is not in a hurry at all. It is not too strongly attractive. Make sense? Now if you take a diamagnetic material and keep it even like this, it will try to run away from it because it wants least magnetic fields getting through it. Get it? So it's like some people are, some people find it easy to make friends. It's like making friendship. I am like this. Some people are like this. Like if there is a gathering, they will just go to some nook and corner and do something on their own. They won't interact with anybody. They'll just keep aloof. They won't talk to anybody. They don't like the act of making friends. They're dia. I am probably like para, which is like not too much of a fan of everybody. But I have some whose frequencies match with mine, and we are in resonance, and so we click together. Not everybody. Not everybody. There are some people who are to my liking, and they like me, and therefore there is a little bit of. So, mu r is the relative permeability, and that tells you how many times stronger than the magnetic field can become in a ferromagnetic material. So para and diamagnetic materials are absolutely not put into any use in reality. These are not absolutely useful at all, although they are magnetic materials. And ferromagnetic material is the only thing that basically we are talking about. Now, steel, iron, those are ferromagnetic materials. So both of them have a good amount of relative permeability. Any questions on this? So what's the formula for magnetic, without looking at your books, can you tell me what's the formula for magnetic field next to a straight infinitely long wire carrying current?
Mu naught I over 2 pi a.
Mu naught I over 2 pi a. Now be at center of flat circular coil carrying current. The B at the center of a flat circular coil carrying current. Now when you say flat circular coil, a coil can be just one turn. Or you can have n turns, right? So this is what you're talking about. It's a flat circular coil. Flat means like it's on the floor. It's like in one place. So if you have a flat circular coil of n turns and of radius r, so here is where I like to use r, not in the other one, because there it doesn't make any sense to use r in the equation. That's why I use a. Make sense? The book uses r for that, which doesn't make much sense. Yeah, r is good for this because it's a circle. And the current that is flowing is I. It's flowing everywhere, but the current that is entering is I. Now first tell me, which way is the magnetic field at the center? Which way? Remember, you may be... See, he picked up his left hand. Yeah, always when you're searching for the direction, call out that rule properly. Right hand grip rule. Call it like that. Then you won't forget this. Right hand grip rule. Don't blindly take up any hand that's free. So which way is the magnetic field? In. And the strength of this magnetic field is mu naught Ni over 2R. Again, this is derived by using calculus, but it's easier derivation. This is an easier derivation because all the little current elements are at the same distance, unlike the other one. You understand what I'm saying? All the little current elements are at the same distance. So your limits are going to be from 0 length to 2 pi r n whole length. So we go from limits 0 to 2 pi r n. And that's how you derive this one. And so this is the equation mu naught Ni, n stands for the number of turns, I is the current that's flowing through it, r is the radius of this turn. So remember this equation. We're not deriving this, but just understand this equation and know how to use it, when to use it. You'll see more. This is the B at the center of a flat circular coil carrying current. Good? And then you have this B along axis. Oh, cut that down.
Oh, sorry. I just got the sound set up.
B along axis of a solenoid carrying current. A solenoid. A solenoid is basically an extended form of the same thing that you saw earlier. What is the earlier one? Flat circular coil. Now think of it as extended. So this is a solenoid. So if the current is going this way, which way is the magnetic field? If the current is going round and round, which way is the magnetic field? Is it to the right?
Going to the left.
It's difficult. Because it's a two-dimensional board and I'm drawing a 3D object there, which wire is actually coming in front? Is this coming up from behind and this is in front, or this is going from front and going behind? You can't tell. So normally you won't get confused with these kind of things, so you won't be given a drawing that is as bad as this. So if you're actually supposed to find the directions, you'll be given more clear drawings, like on a hollow tube, they'll wind the wires like this. Now, that is a solenoid. Can you see which way the current is going? It's going from inside, coming out. It goes from inside, comes out. So basically the current is going this way. Use your same rule. Which way is the current going? Imagine these are your fingers. So go like this and grip it. You get it? So these are the currents. So the tip of your fingers are acting like currents. Grip it like this. Which way is the field? So the field is going along the axis. So which is the north pole? This one or that one is the north pole? So that's going to be acting as a north pole, this is acting as a south pole. So when the current goes like this, when the current goes from behind, like this, in this manner, so if I'm going to look from here, it's clockwise current, right? If I'm looking from this side of the tube, it's going to be clockwise current. And if I look at the same thing from here, it's a counterclockwise current. So it's got more depth perception. So the strength of the magnetic field inside there is given by this equation, mu naught nr. Now remember again, I'm writing mu naught assuming that there is nothing inside, correct? It's just air. If it is just a hollow tube, then it's just mu naught. But if it is not a hollow tube, suppose it is this, imagine a solid rod and then I'm winding it on the solid rod, then the formula is going to be mu naught times mu r. You have to use that. Now what is what? This is the strength of the magnetic field along the axis, that's what I wrote here. And this is your permeability of free space. And what is N standing for? N is the number of turns per meter length of solenoid. Number of turns per meter length of the solenoid. What does that mean? That means if the length of the solenoid from here to here is L, and in the whole length, if I have N turns, it'll be N over L. Correct. That's going to be the N over L. B equal to mu naught Ni. That's an important equation too, where N is this. Number of turns per meter. So if I have so this is basically a solenoid. This is a solenoid. That's a solenoid. Now if I'm going to pass a current through it, what is going to be in the center is a magnetic field along the axis. Make sense? Now what will happen to the magnetic field if I do that? It will increase, decrease, stay the same?
Decrease.
Decrease. Because the number of turns per meter is lessened now. What if I do it like this? It's got too many turns per meter, right? And therefore it will be bigger. So the strength of this field actually will be depending on how compressed they are. The strength of the field will fluctuate. So if I send a wave, a compression wave like that, the strength of the field will be changing all over the place. Make sense? Yeah, so this is an equation for the strength of the magnetic field along the axis of a solenoid. Now coming to the other one, which is like you already know how to use Fleming's left-hand rule. So let me give you some questions here. If this is a current carrying conductor, carrying current that way, and the magnetic field is that way, which way is the force experienced by it? So take up the Fleming's left-hand rule. Oh, you're not gone through it?
No.
Okay. All right, just to give you an idea again now, I thought I touched on that topic. So between this north and that south, imagine there is a magnetic field. There's a magnetic field like that, right? There's a magnetic field going from here to there. Suppose there's a wire here carrying current into the board. If there's a wire there carrying current into the board, won't that wire have its own magnetic field around it? So this wire will have its own magnetic field around it. So this has a magnetic field around it. And when this magnetic field comes in, will it disturb this magnetic field? Yes, because you're having now multiple magnetic fields. So what will be the end consequence? The consequence is the magnetic field lines will be distorted like that. And all these fields will be like crowded like that on one side. You can see how it goes with the flow. And these are going to be repelled from there. Why? Because this is going that way and that's going this way. So the net magnetic field here is 0. Because this magnetic field is going that way and that magnetic field is going that way. So the net magnetic field here is going to be 0. Whereas here the lines are all crowded. Now, crowded lines will try to always repel each other. A crowded line over there, they'll try to push away from each other. So what will happen to this wire? Which way will it experience a force? Downward. So this wire is going to experience a force downward. When? When a current flows into the board and the magnetic field is that way. Now, to find out the direction of the force, you can't be drawing these magnetic fields all the time. That's why we use the Fleming's left-hand rule. So how to do it, right? Take your left hand first. Fleming's left-hand rule. So take your left hand, like put these fingers at right angles to each other. Don't hold it like that. You hold it like stiff and firm like this. All right? Now what do each finger represent? That is the force. You know this. The thumb is the most important, right, part of your hand, because this will support a lot of force. So this is basically the main support. Without this thumb, you're going to have trouble. I think you did some experiment, right, with Mr. Budniak? Yeah. This is force. So that's why I'm doing force for the thumb. Thumb is force. And this is magnetic field, telling the direction of magnetic field. So you point somewhere. Pointing finger is the direction of the magnet. And this is the current. So what is that? F, B for magnetic field, and I for current. FBI. You're picking up the wrong hand.
Left hand.
All right, left hand. So pick up the proper hand. Pick up the, not right hand, pick up the proper hand, which is your left hand here. So this is force. You can also do it as father, head of the family. Mother, giving all the directions. Do this, don't do this. And I. You are in the middle of them. So father, mother, I. F, M for magnetic field, I. You can learn it any way you want, but this is what it is, FBI. So, how to use this? Because you can't be drawing this to figure out which way the force is going to be. So, use this properly. Now, how to use this? Many students get confused on this. How do you have to do this is first orient one of the directions according to what's given. Then hold it there and then align the next one. Say, for example, the current is upward. So, which way will you put this finger? This is actually going upward. That's fine. And then I told you the magnetic field is going from this end of the room to that end of the room. So what students do is, oh, magnetic field is going that way. And this is okay, magnetic field.
Oops.
What has happened now is you're not holding this one steady. So what you have to do is first align the current and then hold it there and twist it such that that one goes there. So which way will this experience a force? Get it?
That's hard.
Yeah. And understand for positive charges, you just do the same thing. But for negative charges, remember if electrons are going that way, which way is the current? So just remember that part of it.